So with that kind of high level motivation, I'll kind of now ground things very specifically. In this talk, I would like to kind of focus on a very specific aspect, which is admittedly very narrow, but which is feature learning. And so what is like the main kind of interesting thing here, which we've gotten used to, but honestly is still kind of surprising, which is like basically we do supervised learning, right? If you look at these modern neural networks, there's the feature extraction, and then there's kind of a classification on top. But what is interesting is that this happens simultaneously. That's kind of the main thing of deep learning, right? Which is like, you see some examples, right? You see the corresponding labels, and then you train the whole system end to end, but somehow the middle features, right? Like these features are automatically good, right? The penultimate layer, the features are somehow meaningful, and there's various ways to kind of look at it, and they kind of give something sensible. And this, I would argue, is at the heart of a lot of things that we do, common heuristics that we do. For example, like one thing, since I'll talk about it later, one of the most common things in this new wave is like basically transfer learning, right? Like in this new wave of deep learning vision, that's one of the things that kind of like worked much better than a lot of people expected. And so this is the idea that, well, maybe you have a task where you have a lot of data from, and so you do pre-training, right, using the task that you have a lot of data from, and then send basically, again, the idea is that you have a feature extractor and a classifier on top. And so now if you have like a task that is a little bit more specific, like for example, identifying particular species of cats, and clearly there's a Persian bias here. So you would fine tune the model on basically this kind of smaller data set where you have smaller data from. And so the way transfer learning works, the most common heuristic is you kind of freeze this feature extractor from the pre-training task, and then you would just kind of retrain the classifier on this new data set, right? So you can already see feature learning is quite prominent here. I will not kind of bore you with SSL too much, but it actually is quite prominent in a lot of other modern heuristics like self-supervised learning. And then, one thing I do want to mention, because I will likely have some time to talk about this, is that even in the context of in context of modern transformers, one of the things they actually do very well is to localize the relevant features, right? Like, so for example, when it's a bird, like if you look at the attention, basically the attention as weights are actually on the bird, and then bike and so on. So feature extraction, I would argue, also is like a really important part of these modern transformer architectures. In particular, like people have argued, if you combine this with SSL, you get really good features, right? So it kind of like seems to be everywhere. And a lot of other modern heuristics, right, like feature extraction, I would argue is quite important. But like this is a probability seminar talk. So what are the challenges from a theoretical standpoint, understanding feature learning? And you'll be glad to know I will not go beyond one layer at all in this talk. So keep things very simple. And the one challenge is obviously optimization, which is like, this is the experiment that if you have not seen, I think at this point, a lot of people have seen this, but it's quite surprising. So here, the experiment is very simple. We just assume the data is created according to one hidden layer model. And then we fit a neural network of the same size to this data, right? And so if you do this, basically, and if you run gradient descent, you soon figure out that you cannot do this. You cannot find the global optimal. So gradient descent actually goes to local optimal in this case. And so what you actually have to do is what people call over-parameterization. You actually have to add some hidden nodes and then run gradient descent. And then all of a sudden, if you do this, you do actually get. So kind of the first mysterious thing here is like, why is it the gradient descent goes to the global optimal, right? So that's the one aspect we don't understand. But this is not even the most important one, because sure, maybe you can imagine if I have a lot of parameters, I can make training error 0. I can eventually fit any data set that I want. The real challenge in some sense is like that of generalization. Would it actually be able to predict on a new data set, right? So here the cartoonish picture is that maybe the training loss, especially because I add a lot of parameters, has a lot of global optimum. but then which one is good, right? Like the test loss is more like this, where if I start somewhere, I actually get it's like a different global optimum with a good test error. If I start somewhere else, I get like a bad test error, right? And so here really the challenge is like we kind of need to understand the trajectory of gradient descent to figure out like what are the prediction capabilities, what are the statistical benefits of different global optima, and in particular the one that we actually follow by gradient descent or stochastic gradient descent. And finally, I want to say that this is a very nuanced thing, so we have to be very careful. Because even when you're focused on one hidden layers, these are very rich function classes, neural networks. So it actually matters even what hyperparameters you pick. So in the sense that if you don't pick the right hyperparameters, this could be like how wide the network is, how large of a even standard deviation you use at initialization, or even the learning rate, right? You could actually get really weird answers, right? And so here's like kind of like a the demonstration of this. Again, keeping everything simple, like one hidden layer network. So here I have a bunch of data points, right? 3D data points. I'm fitting one hidden layer neural network to these data points. So this is, if I use bad hyperparameters, I get these very erratic surfaces. And you can kind of imagine this doesn't generalize. But then if I kind of use good hyperparameter choices, all of a sudden we get like these very nice smooth surfaces. So I just want to make sure emphasize that actually the choice of hyperparameters is also very key to whether you actually learn good features or not, and whether you could get good generalization. To push that a little bit further, yeah.
Previous slide, when you say you're feeding data, you're just getting representation.
Yeah, literally, like this is like 2D input, 1D output. This is why it's 3D, right? So X and Y axis and this, right? I'm just literally fitting a neural network like this to this data, right? Nothing fancy. So this is, by the way, like I'll focus a lot on scale of initialization in this talk, but you could see this phenomenon with other parameters. And so this is one interesting experiment, which is like you can, again, emphasizing that even by just changing the standard deviation of the random initialization, you can really get different optima. Well, Berk actually did this simulation in the audience. So if you kind of change the scale of initialization, always you hit global optimum, right? You get 0 training error. So here I'm drawing the training error. You can see it's just 0. But test error looks very different, right? So you actually get very different test behavior. And so what is the problem is that existing theory less here. So, even though we've made a lot of progress on the theoretical kind of the side of deep learning and so on, all of the existing theory almost exclusively is on this side. And this is what you may have heard of under the spanner of neural tangent kernels or linear regime or whatever, or lazy regime sometimes. Basically, the kind of argument in this context would be essentially you show that even though the neural networks are nonlinear, they're dynamic in under certain regimes behave like linear on top of certain kernels. So this is why it's called NTK, because neural tangent kernels. Practice, honestly, though, happens more here. So you would use much smaller initialization, you get much better test error, you get much nicer features, right? And so that's kind of the discrepancy that we want to really fix, which is like, kind of like, if you run gradient descent from small random initialization, right, with the right hyperparameter choices, what will happen? And again, I focus here on scale of initialization. You could redo all of these thoughts with width. So this would mean maybe if you use a very wide network, things will be actually bad. That's where most of the theory is. You could also do it with learning rates.
So the practice is also the mean field kind of limits here?
No, this is actually practice is not even, mean field also has its own problems. Initialization is small, but width is too large. So the mean field is also not practical. So it's also extreme. So here it's really like, because don't have such a wide network, a small initialization would be equivalent of practical. Yeah, so and just to demonstrate this very clearly, again, I'll go back to my simple one hidden layer example. And so in particular, this visualization, so which is like, I'm fitting a one hidden layer model to data. And so I could kind of visualize this neural network by points in 3D. So in the sense that for each hidden node, I look at all the ways coming into it, and I view that as a point in this case 2D, because like the input is 2-dimensional. So for each hidden node, I get a bunch of points. Here, in addition, I am actually assuming that the data is actually generated according to one hidden layer network with 3 hidden units, okay? So, and these are those 3 black lines that you see. Those are the directions of the planted model, if you will, right? This is a model that generated data. So now I have a representation of the model as it changes across time. And so I can actually visualize what will happen with different scales of initialization, right? So this is when you have kind of non-lazy features. This is like not the NTK regime. This is what kind of happens in practice. You see something interesting happen. So you start from small scale of initialization. Eventually, all of the hidden nodes align themselves with one of those 3 planted directions, right? So in some sense, you actually have discovered the underlying features here of the model. You found the simple model, and this is why actually this does generalize well, because you found some notion of simplicity, right? Whereas like with lazy features, it's kind of like really interesting. Like they move around a little bit, but you never find the underlying model. And actually, it does not generalize as well. Again, training error does become 0, but the test error is actually quite high, right? It's not completely high. It's as good as a kernel method, but still it's relatively high. And so what we really want to understand is kind of this kind of regime, right? Which is like if we do actually use practical hyperparameter choices, this is the kind of phenomena that we want to understand.
So the curves are just the trajectories of the tree?
Yeah. Trajectory of the hidden nodes as you're running gradient descent, basically. You start small, eventually you converge to one of these directions. Go ahead.
So the last layer of the hidden layers.
So this is one hidden layer, so there's only one layer.
It's like doing some clustering, each node.
Yeah, exactly. So it's like basically all of them should become copy of, at least in direction, copy of one of these 3, right? So the direction aligns itself, like it's not exactly the same vector, but they're all in the same direction, right?
Like this shows the spot, like each one of the points gonna have one of the last neurons.
Yeah, exactly. Yeah. So they will be proportional to one of the 3 planted directions, right? When you do this. And by the way, this example, we still don't have a proof of. Like, it's kind of crazy, like 10 years into theory of that, right? So, but different topic.
Anybody use this to make learning faster, this phenomena?
Not that I'm aware of, but I'm sure, I think there's a lot of potential here, yeah.
I just have a clarification question. When you talk about the scale of initialization, what exactly do you mean?
Yeah, so this is like, when, you initialize at random, but it has a standard deviation, right?
So you say like normal means 0,
Yeah,
but
yeah.
some
It's variance, right? Like that's what I'm talking about. Like how do you change the variance? So a lot of theory becomes much easier if you use a large variance, but like if you look at any of the standard initializations, way below what you would actually use in like some of the theory results. And this is why like the test errors you get out of theory are not so good, basically.
And just a further clarification. So the number of the hidden units, are you keeping that as fixed, or that would be some
here,
semantics?
Yes. So here is fixed, but you could actually play, this kind of theory you could play, they kind of trade off each other in the sense that you could see the same phenomena by picking a lot of hidden units. Again, the network becomes lazy and it does not learn good features when you add a lot of hidden units with a fixed initialization. So they're kind of interrelated. Also learning rate. So if you use a very small learning rate, then the network again becomes slow. You converge the global optimum, but not a good one. So these are really interchangeable, but I will focus on this initialization as like a proxy for all 3, basically.
Is initialization scaling depends on the size of the model, or it's just
I think in principle, yes, right? Yeah. So these again, all 3 are kind of interrelated with each other. So that's why I'm kind of fixing 2, focusing on 1. But you could kind of do kind of most of the theory if you do the other ones, right? Yeah.
Do we see similar behavior in regression when the labels are not?
But this is all regression, right? So I'm actually doing, this is not classification, right? Like, sorry. So the color is actually just showing that the sign of the hidden nodes, but it's not relevant for our discussion, right? Like whether, you put the output layer is positive or negative, that's color coding. Sorry about that.
Is there any label noise here?
No, not in this experiment. Clean data, perfect fit. That even gets more interesting, but I'm not going to talk about it. Yeah. So yeah, that's kind of the surprising phenomena, or like the kind of thing we want to settle. And so I'll talk about this depending on how much, how many questions are in the context of free problems. So I actually start with a low-rank reconstruction problem as a toy example. It's like the easiest class of problems that you could kind of see this phenomenon. Then I'll move to one hidden layers, and if we have time, I'll even tell you about actual transformers, right? Like one hidden layer, though, not too ambitious. So how this phenomenon arises there. So the first one, on low-rank reconstruction, this is like a completely USC project. Dominic was a former postdoc here, and Changzi is a student here. So let me kind of explain how this phenomenon manifests itself here. And there is actually another USC connection. Once we get to the theorem, I'll tell you about. Like one of your recent hires has done it really, or potential hires. Something really interesting here too. So, but here the low-rank reconstruction problem is very simple. You get linear measurements from a low-rank matrix. So like factorized, this is the XY kind of situation. So if you want to kind of like mimic this idea of adding more hidden units here. So here the real data is if you will, is kind of generated according to linear measurements from a linear network, if you will, right? Like, there's some hidden units, right? But if you now want to all of a sudden kind of over parameterize, what do? You just add more hidden units or more factors, right? So in this case, you fit a matrix with a rank which is larger than the true rank. So R is bigger than R star. And it's just very easy regression. You just set up a least squares problem, right? To fit to this kind of model in a factorized form, and then you just run gradient descent from small random initialization, right? So everything is the same, there's just no nonlinearity here, right? So it's kind of like the easiest setup to begin looking at this kind of problems. And so, this problem class is actually kind of interesting by itself. Like, even though it's a simpler problem class, there's still a lot of unresolved questions here, in a sense that, first of all, like if you look at historically how we studied this problem, I've also done a lot of work on this historically. So there's kind of two dominant approaches to trying to understand gradient descent here. One idea is that you come up with some sort of clever initialization scheme. That kind of puts you within the vicinity of the global optimum. This is often spectral techniques, if you will, because they come from method of moment kind of ideas. So you kind of like come up with a clever initialization that kind of statistically is close to the global optimum, you can prove it. And then locally, you can imagine the problem is kind of convex, so you can run gradient descent and show gradient descent works. So that's kind of one class of literature that tries to address this kind of problem. And this is some stuff that I kind of started working on like almost a decade ago now. That's also sad to say. But then there's also like another different kind of approach, which you actually mathematically try to study the landscape in the sense that, these are non-convex landscapes. You try to figure out where are the local optimum, where are the saddles, and so on. And, then come up with clever algorithms that avoid the bad parts of the region, right? In this case, you come up with saddle avoiding algorithms, but they're often not so cheap to execute because you need second order information, right? But it's a different style of analysis that you try to analyze the entire landscape.
You need a stochastic gradient descent?
Yeah, but even stochastic gradients, and we don't know, it works, but we don't know the rates, right? And in fact, even for gradient descent, that's what I'm going to talk about, we don't know it, right? But even despite all of this literature, if you just ask, if I run gradient descent from small random initialization, does it work? Even that is not understood, right? So that is actually, I'm saying despite all of this literature over the last 10 years, if you ask this question, which is, can you get global convergence from small random initialization? At least with reasonable rates, not understood, right? And so that is kind of open. And of course, the real question, I would say, the generalization question is the real challenge here, which is, again, remember, we're kind of in this over-parameterized scenario where we have more parameters than the size of the training data. Like here is the number of the measurements we get, which itself obviously has to be more than the true amount of parameters in like the tandem model. So in this case, it is actually fairly easy to show that training error goes to zero. And in fact, we wrote a paper about this a few years ago, but this doesn't tell you anything, right? Because there are many global optimum. And so you could have training error be really zero, but the test error, which in this case would be just like how good you are in terms of reconstructing this matrix, could be really bad. And then so here's a plot that demonstrates this. And you can see it's exactly like the neural network case, right? So regardless of scale of initialization, you get zero training error, right? So global optimality, no problem. But if you look at the test error, it actually again goes up, right? So exactly the same plot and behavior, right? And so the problem with this kind of theory, right, unfortunately is here, right? It's actually fairly easy to prove this stuff, but it's here, and we want to be here, right?
How does this convergence or this generalization depends on the conditional numbers?
So you'll see a result. It's not so bad. It ends up not being bad, but it's like a polynomial in a condition.
Polynomial?
Yeah.
Then it kind of expected a preconditioning, improve this.
Yes, and actually subsequent work have, by I think we wrote the one, like the first paper we wrote on this was 2 years ago. There is a paper now out, well, this most recent paper is from last year, but there is a paper out now recently where, from University of Chicago and CMU, where they actually exactly show that you can actually improve the condition number dependence by doing some sort of conditioning early in the trajectory of gradients. So your point is perfectly accurate. So you can improve that dependence if you do that. And again, really the challenge is like, can you generalize well when you actually run gradient descent from a small random initialization? We'll see how much time I have to talk more about theory, but basically, I just want to leave you with this main insight before I actually tell you the theorem. The key idea that enables a lot of our results, the recent results in this kind of line of literature, is that what we effectively show is that gradient descent plus overparameterization essentially behaves like running power method on certain spectral initialization. And I'll tell you exactly what it means. But the high level idea is that somehow the initial trajectory of gradient descent mimics basically spectral methods, method of moment methods that people have been using in machine learning for a very long time. And just to be very concrete about this, I'll tell you what exact matrix we do this on later on. But just to be very clear, so I'll compare the trajectory of power method on this kind of matrix, spectral matrix. And again, remember, this is kind of the ideas that we used to do spectral initialization, then run gradient descent. But I'll compare the trajectory. In one case, I'm looking at just, I don't know why the video is not playing, but okay, it's just low. Okay, good. So on the one hand, you have gradient descent. On the other one, you have power method on a spectral matrix, right? Which I'll tell you about later what it is. But you can see initially the trajectories are really on top of each other, right? And all of us can analyze power method. So that's the idea. Like instead of analyzing gradient descent, we'll just analyze power method on a particular matrix, right? Eventually they diverge, but by the time they diverge, it's kind of close enough. So you can imagine at this point you're close enough, and then you can do something else for trajectory analysis, right? And again, this is a slightly different viewpoint where I'm actually literally showing you the angle between the ground truth and the top matrix you get out of power method and gradient descent. And you can see again, initial trajectory, they're really on top of each other, right? So gradient descent is literally running power method on these matrices. And this is kind of like full circle for me because again, like 8 years ago, or whenever we looked at this problem, I would use the spectral matrix and run power method on it to initialize. And it turns out that if you run gradient descent with overparameterization, it just does that exactly. So it's kind of was the right thing to do, but you don't need the spectral initialization at all. Gradient descent just does it for you. And so that is kind of the main insight behind a lot of these results, which is basically early trajectory of gradient descent have certain biases that kind of allows you to analyze these problems. And so, but here's kind of the final conclusion. I'm actually ignoring the conclusion for the statement, the condition number for the statement. So let's pretend things are Gaussian and the condition number is 01. We can remove both assumptions. I just like easier to explain the result here. Like this. So basically the result is that if you initialize small enough, there's an exact formula, but I didn't want to bore you with the details. So first of all, you're in this overparameterized regime. here where are the things a little bit suboptimal. You know, instead of having n being larger than the true number of parameters, it's a little bit higher, it's r star square. But other than that, you know, you pick a step size, you run gradient descent. If you stop somewhere, basically, if you look at the generalization error, in which in this case is the you know, the matrix you find out of gradient descent versus the true matrix, the error goes down with scale of initialization. That's the critical part, right? So if scale of initialization goes to 0, the error becomes 0, right? Which is what we saw in the plots, right?
How that the rate depends on this choice of rank parameter here.
So these are the details that I've hidden,
Yeah.
but it's polynomial, but it's fairly reasonable. So
In practice,
nothing-
how do we choose that?
So how do you choose alpha?
R.
R, so this result works with any R, right? Because you could also run it for any
So
R.
this is polynomial dependence on R, right?
Yeah, but no, in the sample complexity, it's yeah, it's R star square. R doesn't show up. That's actually important here.
Because I don't know that, so in practice, how do I choose this?
So yeah, like this is a general problem in this field in general, right? But basically here we're not focusing on that issue. We're just saying like any R bigger than R star that you pick would work. Gradient descent would give you the right answer. But how do you ensure that you don't pick something below that? You know, you would have to do some sort of cross validation essentially. Go ahead.
Just a clarification, so maybe I don't fully understand. It's like, so how does this depend on the sample size? Like, wouldn't you hope to improve with more samples?
Yeah, so basically you would expect this result to be true with R star times this, right? But I see you're saying like, how does the result improve if you have more samples?
This feels like a optimization error, and
No, this is generalization error because like this is like the model versus the true, right?
X, Y is the new data, right?
Yeah. So this is like the test error on new data, if you will, right? Yeah.
I see.
But do this gives you convergence rates algorithmically?
Yeah. We have race and everything. Yeah. But it's just well, there's different phases, so the race are a little bit different. But the race are actually, I would say, optimal in this result. Like it matches with what you expect to see. But I would say the main weakness of this result is the sample complexity here, which is like you expect this to be R star, but it's R star square. But other than that, again, these polynomial dependencies, maybe they could be stronger, but they're at least in the right direction, right?
Remind me, what is alpha here is?
Alpha is scale of initialization, right? Which is like, you know,
Oh.
so critically, this is what was missing from a lot of the previous literature is like, you know, you could not let alpha go to 0, right? You needed alpha large enough, and then you could say training error is 0. But then the test error, the error you make in terms of reconstructing the matrix would be large, right? The key critical part to focus on in this result is that I can take the limit of alpha goes to 0, and that's what you see in practice.
He also comments, is it possible to consider such approximate message passing algorithm on this?
So potentially, there's no proof of this.
Yeah, I
in
know.
this. Yeah.
So
yeah,
any
but
kind of
that could
empirical
be an
stuff
alternative.
going on to compare.
So there is no proof of AMP with random initialization basically at the moment. So it's not there's no direct comparison we could make in this case.
Practically.
Practically, I think in this Gaussian models, AMP would be faster than gradient descent, but on any realistic measurement model, it would kind of suffer.
So is that empirically a linear convergence or it's
I think AMP relies very much on the statistical correlations being correct. So if you have Gaussian data, it will work out. But if you move away from the Gaussian assumption, it will kind of start failing. Go ahead.
Also, so is there a lower bound on alpha, or this you can let off? I'm trying to understand what prevents you from like letting alpha.
Yeah, so if you, that's a good point. If you let alpha well, there is a trade-off in the sense that if you make alpha very small, right? You cannot set alpha equal to 0 because that's the local maximum, right? But if you make alpha smaller, it becomes slower, right? Because if you start, but it's not that slower because it shows up logarithmically, right? But definitely you cannot make it equal to 0 because 0 is a local maximum, right? But as long as you're small, you pay a little bit in terms of time, right? But other than that, there's no. But this actually does match. Like these dependence. This one, I'm sure it's not correct because like a random polynomial 3 to the 5, right? But 3 over 5. But this dependence empirically also seems to be correct. Like it is actually very small dependence. Now the good news is this is something that actually has been missing in all of the non-convex literature. this dependence R star square. Again, your most recent recruit, potential recruit in the math department, along with my former postdoc who's also on this paper, they've actually managed to, using very clever arguments, very clever coupling arguments, they've actually brought this down to R star, which is like very fascinating. So you should look out for that. And hopefully you do manage to hire him. So, so that's very exciting. So this graph has been.
So how does that sigma mean XY transpose depend on dimension D1, D2?
This is this is just the ground truth matrix. So
Yeah, so if we scale the dimension for D1.
So, but this is the ground truth, so like it could be whatever, right? Because this is just the underlying low rank matrix. You know, it's right. Like it could be very small, it could be very large, right? But this is just the dependence here, right? And this dependence again, I believe is correct, right? You do need this to depend. So in the sense that if it's actually zero, you will have trouble. Yeah.
What is mu sigma mean?
Mu is the learning rate. Sigma mean is just, this is the minimum eigenvalue of the matrix you're trying to reconstruct. Yeah.
But the minimum is not the zero one, like
Singular.
Yeah, the first non-zero one, yes.
Yes, non-zero.
Exactly. But if it goes to zero, if it's like in the limit of very small, obviously you have to pay for it, right? If your matrix is very degenerate and you're trying to reconstruct, it will take longer to reconstruct. So this dependence is correct. You can actually also think about it like, then you get, your trajectory gets very close to saddle points and it will take a long time to escape them. So this is actually correct behavior, I would say.
Any comments if it's possible to consider some versions with momentum, you know, to.
Yeah, I haven't looked at that, but yeah, for sure, momentum would be better. You know, I think the problem with momentum, and maybe it's actually a very interesting question to study, is I don't know this initial trajectory, how, you know, that part will likely change with momentum and will have a different spectral bias. And so we haven't analyzed that. I mean, we haven't even tried, but that would be, I think the biggest change is that even the spectral bias phenomenon may show itself completely differently if you add momentum, you know, but in practice, it would definitely work well and works better, obviously. Yeah. But it's an interesting question to study theoretically. And so maybe some comments here about the literature. So you don't need the Gaussianity, you can actually go to IRP. So I do want to mention, even when you don't overparameterize, this is the first result that actually shows gradient descent from random initialization works deterministically, right? So even if you did not all care about overparameterization or generalization, this is the first result that did this. Now, you know, there are some random results in the Gaussian case, in this case, which are based on leave one out, but this is kind of the first deterministic result, if you will. The other extreme case was also looked at. This was actually called best paper of ours a few years ago, a couple of years ago. Extreme overparameterization, where R is equal to D. So this result has some caveats. In particular, one that I want to mention, there's many technical improvements compared to that one, but maybe the only thing that I want to mention is that even in this result, you could not set alpha to go to zero because the way the result works, the sample complexity would go to infinity. So like you could not actually let alpha go to zero with finite sample complexity in this even specialized case. So that's kind of like one of the key distinctions. But even if you do heavily overparameterize, the rates and so on are also much better. So, but I just wanted to mention that.
Yeah, one more question.
Sure.
If I want to add like non-negativity constraints on the matrix factors, then what do you think about you know, this random initialization impact? You know, this.
I think that's an interesting question. I honestly not thought about constraints, but actually that would be very interesting to look at. Again, I would you know, like want to know like how it will affect the initial phase, which I think the hardest phase to analyze for that, right? In the later phases, I would have some ideas how to analyze it, to say in a sense that I could kind of roughly tell you how much reduction in sample complexity.
If you get a pattern approximate right, the
Yeah.
convergence will be much
But
easier.
this might actually also be a good problem to think about in the context of your K-means problems.
Yeah,
right?
we
So-
do exactly the same.
Okay, cool.
Yeah.
So we should discuss that more. But it's very interesting. So I'll kind of skip this because the technical side, one of the really challenging things here, especially when you don't have symmetric factors, is like trying to show that like the factors remain balanced, but it's very technical, and so maybe I'll skip this in the interest of time. But I do want to give you a really brief proof sketch just to kind of, because I talked about these spectral matrices, I never really defined them. So first of all, there is a reduction to the symmetric case. It's actually very pretty and nice, but I'm not going to do it. So I'm going to pretend that things are actually symmetric. So the factors, the underlying matrix is symmetric and the factorization is symmetric. But the key question I want to give you ideas about is how does small initialization help here, right? And for this, we're going to look at just the first gradient iteration. So you have to believe me on this simple math, right? This is what the gradient looks like. So if you initialize small, roughly speaking, what happens is you can ignore this matrix, okay? Because if this is at initialization is small, like you can ignore it compared to this matrix. And so you end up with a fixed matrix times U0, okay? So the first iteration of the gradient. So if you plug it back into the gradient descent update, then you actually end up with identity plus step size times this fixed matrix times U0. So fixed matrix times U0. So that seems interesting, right? So and you can imagine this approximation is not only true for the first iteration, but as long as U is small, it's kind of the same thing, right? I can still ignore it. So for small t, actually, you just end up with fixed matrix to the power t times U0, which is of course the power. Of course, you know, you have to make these approximation precise, but the intuition is actually very easy, right? So now you might ask like, okay, so why is it that I run power method on this matrix? Why is it any good, right? So this is actually why it's good, because in this case, you can actually show that this matrix with high probability, it's a random matrix, for example, when it's Gaussian. Under RIP, you could also show this, but basically it concentrates very well around the ground truth matrix. So actually, it's as if I'm running power method on a ground truth matrix, right? So that can't be a bad thing, right? So that's why it works, right? So basically, you know, gradient descent at least aligns in terms of the subspaces with the ground truth matrix in this initial phase. That's why it's good. And surprisingly, this not only happens in this model, but a lot of other models, as you will see. That's kind of the critical idea. So the initial trajectory of gradient descent kind of mimics a spectral method, a method of moments. And so it reveals something interesting about the underlying structure in the data. So that's the critical part. And so again, like, you know, this kind of exposition makes it a little bit easier than it actually is, unfortunately, in the sense that there's actually 3 phases in this kind of problem. There is this spectral alignment phase where you kind of show these eigenspaces align themselves, but you have to do a little bit more work toward that. So there's actually 2 other phases. One is like a sort of a saddle avoidance phase where, you know, saddles here are degenerate eigenvalues of this matrix that you're trying to reconstruct. So basically, there is a phase where you actually have to show certain minimum eigenvalues grow so that you can avoid saddles. And so this is what we're depicting, and like you see that growth. And finally, you are actually legitimately within a, you know, a small distance of the global optimum, and then it's kind of more standard, right? You kind of like almost convex, but not strongly convex scenario. You can kind of just, you know, go back to the convex analysis for that. So that is kind of what really happens. So that is kind of like the story for low rank stuff. I did a little bit more proof here because kind of maybe the model is easier to understand. If there are any lingering questions about this, I'll kind of move to the neural network setting now. Okay, so we can move on. Yeah, this part is focused on one hidden layer neural networks. So this is actually joint work with Alex Damian and Jason Lee at Princeton, this part. Also a former USC colleague, I guess. So in this case, we want to kind of like, okay, we did it for, you know, low rank models, which is kind of linear networks, if you will. Now we want to actually go to like at least one hidden layer neural nets. And there, well, actually Alex and Jason and another student, they've also now done it for 3 layers if you wish to go deeper. But I think the underlying ideas are similar. So we're going to study how you could learn polynomials using neural networks, right? Just as a function class to learn. So what is the setting here? We're going to assume the input data is Gaussian, and then you have the sort of polynomial functions of this input as your labels, right? So here, I'm going to assume you have a polynomial of degree p, and then and this is kind of your feature matrix, if you will. Here you have like a fat matrix, R is less than D. So you have a linear embedding, if you will. So this is kind of the feature layer, and then you have a nonlinear polynomial of degree p on top of it. So that's how the labels are created from the input data. But of course, the model you fit to this data is still a one hidden layer legit ReLU network, right? So now we want to kind of study what again happens if you just run gradient descent from small initialization in this case, right? So go ahead.
Just a clarifying, so you're talking about labels, but are we still in a regression setting?
Yeah, this is regression, sorry, like you could say output. I don't know the right word for all things.
Response.
Response, yeah, okay, R, yeah. You remembered R, but yes. That's needed to pay attention more in statistics classes. Maybe so much too, so. But in any case, so thank you. Now, so here's our result. So this is in particular, one reason this class is interesting, by the way, is that, in this case, it is actually very well understood in a lazy or kernel regime what happens. And so here's a result, 2020 result by Andrea Montanari and his group, where they actually studied what happens in the lazy regime. And they show that even if you have many, many hidden units, regardless of size of hidden units, you would need at least D to the P many samples to get, small test error, right? And so D is this larger dimension, the input dimension in this case, and P is the degree of the polynomial. So this is the best you can do in the lazy regime. If you use large initialization, in this kind of lazy regime. And so to contrast it, so this is our result. If you actually run gradient descent from small random initialization, this is the kind of result that you get, is that the generalization error actually goes down fairly reasonably. Critically, this depends on R to the P, right? So it's actually an exponential improvement, right? If R is sufficiently smaller than D, right? So it actually depends on a smaller dimension to the P if you run gradient descent from small random initialization. So really the contrast here is that in one case, you need D to the P many samples, whereas here you need kind of R to the P many samples. And if you really think about this problem, the sample complexity should be R to the P plus D times R, right? Because you kind of need to learn U and you kind of need to learn G, right? And so that's roughly the number of parameters, right? And so unfortunately, this is D squared, so it's a little bit suboptimal, but this one is kind of correct. It's kind of order R to the P. And so this is very vivid that you actually get this feature learning improvement, right? Because you literally learn the features U with much lower sample complexity. If you're in this, sometimes they call it the rich regime or the non-lazy regime, because you learn samples more effectively, features more effectively. So that's kind of the main result, but you can also take this and legitimately do it in a transfer learning context now, right? Once you kind of have this result, in the sense that what is kind of the simplest transfer learning setup that you can imagine, which is like I have a source data and target data. You have a lot of source data called a little n, a little bit of target data, capital N. And so in this case, if I want to follow this toy model, what we're going to do is that we're going to assume source and target data have the same features, right? The same representation. So U is shared, but then the polynomial heads are actually different, right? So basically I have different kind of polynomial heads, but both of them are of degree P, so U is shared. So what you do in practice in this context would be that you train both layers on the source data, right? Gradient descent, this is how most of the transfer learning heuristics actually work. You train both layers on the source data, and then you freeze the features, as you remember from the early slides. So you keep the first layer fixed, but you retrain the last layer, right? So that on the target data, right? And so that is the setup we actually follow. So if you do this on this kind of data model, this is the kind of generalization error that you would actually get. Again, this is actually a minimal number of hidden units if you think about this problem. So you get like two sources of error. One is like the amount of data you need to kind of learn the representation from source data, right? So again, this is just kind of like before, right? And then this is the amount of data you need, target data, to kind of learn the new polynomial. The critical thing to focus on, there is actually no dependence on dimension here, right? So it's as if you've really learned the polynomial head. You've learned the representation from the source data, and you just need to learn the new polynomial head, right? And that would be the sample complexity. So the amount of target data you need is much less because you just need to learn the new polynomial head. You don't need to know anything about the features because you've already learned them, right? So this, I would argue, is the correct kind of dependence in a transfer learning context. You learn the features, you just relearning the new polynomial head. So it looks like I'm kind of running low on time. So I kind of will skip transformers, but basically because that will take actually honestly much more than this. But but basically it turns out that you can actually even do this in the context of transformers, and in particular, you can literally prove one hit, at least on simple models, you can literally prove that this feature extraction, key feature extraction property does happen, in the sense that, maybe I can kind of go to the very end and show you the simulation. A little bit over ambitious, sorry.
Another talk.
Yeah, another talk. I kind of guessed this would happen though, so. But basically, in a sense that you could actually literally, this is a very simple example where we embed basically the C4 images in random image and noise, and so if you look at the attention layers, they will actually focus in this kind of classification problem. They would actually focus on the relevant features. And so this is something that we can actually prove with simple models, and one hidden layer already, that the attention scores will exactly only pick the relevant portion of the features. They will kind of ignore the rest, right? And the way we do this is, again, using kind of similar theory. It's kind of like we look at the initial trajectory of gradient descent, and that's where you can use to show this kind of phenomenon.
So this attention has this number of the the R in the previous example.
So here, the attention scores here is basically like the relative importance of the different features in the model. And
you have multi-head attention here, right?
Yeah, this is single head. Sorry.
Single.
Yeah. So there's multiple layers, but this is just like the penultimate layer. But that's actually like something we're working on, how to make this stuff multi-head. But so maybe to kind of wrap up. So basically in this talk, I kind of tried to discuss some theoretical foundations for feature learning. The critical component that actually this is very new, right? And we've been only able to do this in the past couple of years, still very much ongoing, is like, how do you go beyond this lazy feature learning, which is like the dominant theory in neural networks. And so we've been able to actually push this quite far, perhaps surprisingly. We now can do this for low-rank problems, one hidden layer, and even some simplified transformers. But there's a lot of things to do, honestly. But the key idea that I want to leave with is kind of what I said at the beginning, which is like the key idea driving all of these results is that the initial trajectory of gradient descent has certain interesting spectral biases and implicit biases, if you will, that actually kind of reveals something about the ground truth. And so that is kind of the key driving idea. Hopefully, this kind of intuition can also allow us to do some more useful things based on this intuition. And just with that, I can get here.
Thank you very much.